Very good morning dear students, welcome to Purnachandra Higher Secondary School. Okay, so in this video session we are discussing about the next portion of your chapter number 4. Okay, so that is your laws of motion. Okay, so that is in this session we are discussing about the conservation of linear momentum. Okay, impulsive force and impulse. Clear? So first of all we are discussing about conservation of linear momentum. Clear? In the previous video lecture I have already told you that what is linear momentum. Okay, the linear momentum, what is the representation, what is the mathematical representation of linear momentum, what is the physical significance of linear momentum. These things we have discussed in our previous video lecture of laws of motion. Clear? So kindly verify it, kindly look at the videos very carefully and subscribe it. Okay, so now conservation of linear momentum. So what the principle says that the conservation of linear momentum, the principle says that if there is no external force is applied on a system, okay, that is in the absence of any external force, clear, the net or the total momentum of the system remains conserved. This is the statement. Clear? So what is the statement? I will repeat another time. In the absence of the external force, the net or total momentum, okay, of a system becomes conserved. Clear? So this is the statement of your conservation of linear momentum. Clear, all of you? Okay, so now we have to so this is the statement. So now we will mathematically verify. Okay, now we will mathematically verify the conservation of or the proof of your conservation of linear momentum. Clear? So this is the proof of conservation of your linear momentum. How it can be proved? Just have a look at it. Okay, so from the Newton's second law, what we will know? Now we will know the definition of your force. Clear? And the magnitude of your force. Clear? So from this, or from Newton's second law, we know that what we will know? Now the force is equal to mass into acceleration. Yes or no? So from the Newton's second law, we know that the force is equal to mass into acceleration. Clear, all of you? So that implies I can write F is equal to m. Now the acceleration can be represented as rate of change of velocity. All of you know the acceleration can be represented as rate of change of velocity. So now this is dv divided by dt. Clear? So that implies now F is equal to, now let us take the mass as it is a constant with respect to time. So that's why I can take the mass into the derivative. Okay, so I can write it d by dt within bracket mv. I can write it because it's a constant with respect to time. Okay, so now that implies F is equal to, now what is mass into velocity? We know that in the previous class or in the previous video lecture, what is mass into velocity? Now mass into velocity is nothing but your linear momentum. Very simple. So that means I can write it here in place of, we know that is the linear momentum T is equal to mass into velocity. So in place of mass into velocity, we can put dP divided by dt. Understood, all of you? So now what I will get? I will get the rate of change of, look at it very carefully, the rate of change of linear momentum is nothing but your force. Clear? So this is your Newton's second law. Okay, so now what the statement says of conservation of linear momentum, because this is the aim, we have to prove this. So what the statement says? Now in the absence of any external force, that means there is no external force applied on it, then what is the value of F? Simply 0. So if F is equal to 0, if F is equal to 0, then what I can write? Very simple. I can write that implies dP divided by dt is equal to 0. dP divided by dt is equal to 0. So that implies what is the value of linear momentum? Then I can write it as this derivative is equal to 0, that means the p value must be a constant, because this derivative is equal to 0, and when we will find out the value of p, what we will do? We will have the integration, and the integration of a constant becomes 0. Clear? So p is nothing but a constant. Clear, all of you? Okay, so that implies if p is a constant, then I can write it here, that is p initial is equal to p final. This is I can write. Okay, so p initial is equal to p final. That means the momentum in the system, the momentum initially of the system must be equal to the momentum after the process. Clear? That means the whole. So this statement, suppose I will name it as the statement number 1. So what is the equation 1 of statement 1, or this mathematical statement of number 1 says that? Now it says that the total or the net momentum of a system becomes conserved. Clear, all of you? Okay, that's why it is initial momentum is equal to final momentum. So that's why total momentum becomes conserved. All of you clear? Okay, so now, so this is the conservation of linear momentum proof. We know that how the in a system where the external force becomes 0, the total momentum becomes conserved or constant. Clear? Okay. So now what is the application actually? What is the physical application of this conservation of linear momentum? What is the physical application? The important physical applications, there are various type of physical applications. So for the first one I can tell you, suppose I can tell you that suppose recoil of gun. The first physical application I can tell, number 1 is recoil of gun. What does it mean? What this phenomenon says recoil of gun? Now recoil of gun actually based upon the conservation of linear momentum. Okay. So what are the, in this process recoil of gun, suppose let us discuss about the recoil of gun better. We will discuss about that recoil of gun. How it happens? Look at here. Recoiling of gun. Okay, so we are discussing about the first application. This is the only the important application, recoil of gun. Okay, so what the recoil of gun means? The recoil of gun means, suppose we will assume that the gun and the bullet inside the barrel. Listen very carefully. The gun and the bullet inside the barrel of that gun becomes isolated system. Becomes a isolated system. Suppose we assume that both are in the isolated system. Okay, both are isolated system. Then when they are at rest, when the bullet is not fired, then what happens? The bullet will not move. The gun will not move. That means initially the velocity becomes 0, because the both bullet and gun becomes at rest. Clear? So what is my momentum? Let us find out. Okay, and after firing the bullet, now suppose the bullet is fired from the barrel of the gun. Okay, so now if the bullet is fired from the barrel with some velocity, then with this effect of the motion of the bullet, the gun recoils to the backward direction. The gun recoils to the backward direction. So when the bullet moves in the forward direction with some velocity from the barrel of the gun, then the gun recoils to the backward direction with some velocity. Clear? Okay. So now we told that this is the application of conserved linear momentum. That means before fire and after fire, both the linear momentum becomes conserved. Clear? Okay. So that means let us find out what will be the velocity of the gun. That is the recoiling velocity. Let us find out. Let us discuss about the recoil velocity of the gun. Okay. So now we will assume that suppose there is a gun, any gun. okay, and the gun and the bullet. Listen very carefully. The gun and the bullet both are at rest first. Okay. So first of all, we have to find out initial momentum, that is P initial. Okay. So P initial we have to find out. So before that, let us take the initial velocity. The initial velocity of the gun becomes uc. The initial velocity of bullet becomes ub. The mass of the gun becomes mg, and the mass of the bullet becomes mb. So we will assume that let the mass of the gun becomes mg, the mass of the bullet becomes mb. The initial velocity of the gun becomes uc, and the initial velocity of the bullet becomes ub. Clear? So we have to find out the initial momentum of that system first, because both the bullet and the gun are, we will assume as a isolated system. Okay. So now isolated means separate one. Okay. So now what I can write, we know that your P, the momentum P is nothing but your product of mass into velocity. So let us find out what is the initial momentum of that system. Let us find out. So what I can write, now mass of the gun into velocity of the gun plus mass of the bullet into velocity of the bullet. This is the formula actually. The initial momentum before firing of the gun. This is the expression of your linear momentum. Very simple. This is the expression of your linear momentum. Clear all of you? Okay. But we know that before firing, both the bullet and the gun, they are at rest. That means what is the value of this? The value becomes 0 simply. So initial momentum of the system mguc plus mbub is nothing but your 0, because both are at rest. Clear? So this is my initial momentum. Understood? So now let us find out what is my final momentum. What is my final momentum? PF. Suppose I am estimating PF. Okay. So before finding out the PF, again we will assume that after firing, listen very carefully. After firing, okay, we know that the mass of the gun becomes mg, the mass of the bullet becomes mb. So after firing, the bullet will be fired with the velocity. Let the bullet will be fired at a velocity vb, and the gun recoils to the backward direction with a velocity vz. Understood all of you? Again I will repeat. Let we will assume that when the bullet is fired in the forward direction with a velocity vb, the bullet will be fired in the forward direction with a velocity vb. Then the gun recoils to the backward direction, okay, with a velocity vz. So now what is the momentum says? After fired, similarly the mass of the gun, the velocity of the gun plus the mass of the bullet, the velocity of the bullet. Clear? So this is the case. So before firing, this is the initial momentum. After firing, this is the final momentum. And we know that the whole system in the recoil of gun, the whole system satisfies the conservation of linear momentum. So we can write by conservation of linear momentum. Okay, by conservation of your linear momentum, what we can write? Now we can write that P initial is equal to P final. Very simple. P initial is equal to P final. We can write. So that implies what is the value of P initial? Now P initial becomes 0 because both are isolated one and both have become rest. Okay. So 0 is equal to the PF becomes this one. That is mgvg plus mbvg. Understood all of you? Okay, so that implies I can write mgvc is equal to minus mb/vb. Clear? So that implies we have to find out the recoil velocity of the gun. With what velocity it will recoil back? Which one? Gun. The gun will be recoiled. Bullet will be fired to the front or in the forward direction. With this effect, the gun recoils back. Okay. So Vz is equal to minus mb/vb divided by Vz. Divided by mg. Okay. So Vz is equal to minus mb/vb divided by mg. Understood all of you? Okay. So that means this, I will name it as equation number 2. So what the equation number 2 says us? The equation number 2 says us or gives us the recoil velocity of the gun. That means the velocity of the gun with which it will be recoils back. Understood all of you? It's very important. It's very important. By conservation of linear momentum, we know that P initial is equal to P final. So by applying these two, we can get the recoil velocity of the gun. All of you clear? Okay. So this is the recoil velocity. Recoils back. The gun will be recoils back with this velocity Vz. Understood all of you? Okay. And what conclusion we can derive from equation number 2? Look at very carefully. What conclusion we can get? The first conclusion is that as there is a negative sign, look at here, as there is a negative sign, the gun always recoils in the opposite direction of the bullet. If the bullet is fired in the forward direction, then gun always recoils to the backward direction. Number 1. Number 2, if we will increase the mass of the bullet, listen very carefully, we will increase the mass of the bullet or greater the mass of the bullet and greater the velocity of the bullet, then the recoil velocity of the gun becomes more. Whereas if the mass of the gun is more, then the recoil velocity of the gun becomes lesser. So these are the 3 important conclusions we can get here. Understood all of you? Okay. So this is about one of the important application of the conservation of linear momentum, that is recoil of gun. Understood all of you? Clear? Okay. So now we will move into our next part. We will move into the next part, that is your impulsive force. Impulsive force. We will move into the next part, that is your impulsive force. Okay? So first of all, we understood what is impulsive force. Clear? So listen very carefully. The force which acts upon any body or object, okay, for a very certain period of time. Again I will repeat, the force which acts upon the object or the body for a certain period of time, but unable to change its position, so also direction, okay, change its position, so also its direction with a greater extent or with a larger value, okay, then that type of force is called your impulsive force. Understood all of you? So again I will repeat the statement, listen very carefully. The force which acts on the body for any certain period of time, but it is unable to change its position, velocity and direction of the object of the body in a greater extent or in a greater value, with a greater value, okay, then that type of force is called your impulsive force. Okay, so What is the example? Let us take the example. Suppose a player is going to bat. Okay, and so there is a connection of bat with the ball. There is a connection of bat with the ball during the cricket match repeatedly, but the connection is only a certain period of time, very small period of time, shorter period of time. But due to this connection, the ball can be moved to the outside the boundary. It become a 6 or it became a 4. That means that force which the bat applied on that ball for a certain period of time, that type of force is called your impulsive force. Another example I will take during the football match. Okay, the force applied by the foot of the footballer to the football, that type of force is the impulsive force, because due to the force of the foot of the footballer, okay, the football player, okay, the direction or the position of the ball changes repeatedly and with a greater extent. So that type of force which applied by the foot of the football player with the ball, the football, that type of force is called your impulsive force. Understood? So these are the two common and important examples of your impulsive force. Understood all of you? Clear? Okay, so this is the example of your impulsive force. Okay, so one is the force applied by the bat, okay, on the ball, on the cricket ball. That is a impulsive force. Number 2, the force applied by the foot, okay, of the player on the football is an example of an impulsive force. So these are the two important examples of an impulsive force. There are also so many examples of an impulsive force. Understood? So this is your impulsive force. Okay. So now next we will discuss about impulse. Okay, we will discuss about impulse. Okay, so now let us discuss. We will discuss about the impulsive force. Now we will discuss about the impulse. It is denoted as I. Okay, the impulse is denoted as I. So now what the impulse says actually? What the impulse says actually? Okay, so the impulse is provided due to the, listen very carefully, the impulse we will get, or the impulse is produced, okay, by the application of your impulsive force. Understood? So impulse is received by the body when the average impulsive force is applied on their body for a shorter period of time. Again I will repeat, the impulse is received by the object or the body due to the application of your impulsive force, okay, on that body for a certain period of time. Clear? Okay, so that means we can write the impulse I is the product of the impulse, the average impulsive force which is applicable for a certain period of time on any object. So I is equal to F average into T. Okay, so I is equal to F average into T. So when average impulsive force is applied on an object for a certain period of time, then the impulse will be received. Understood all of you? then the impulse will be received. Then for example, we can take suppose during a cricket match a fielder catches a ball. So what actually the fielder do when he will catch the ball? He just lowers his hand. He just lowers his hand to catch the ball. Why? Because due to this, the jerk or the hurting due to the ball, motion of the ball becomes less. Because if he will not lower his hand, then the hurting or jerk by the ball becomes more, and the player will hurt much on the hand, or the impulse value will be more. So to lower the impulse value, the fielder should lower his hand to catch the cricket ball. Understood all of you? This is in one example. Okay, that is the impulse I is equal to. So impulse is nothing but the product of average impulsive force into time. The time for which the impulsive force acts on that object or body. Clear? That is I is equal to F average into T. All clear? Okay, understood? So that is impulse is equal to this much. Now suppose here we are going to discuss a very important part. Suppose we are assuming that an impulsive force F, listen very carefully, we are assuming that an impulsive force F acted on an object for a small period of time dt. Again I will repeat. Suppose we'll assume that let impulsive force F act on a body, okay, for a shorter or small period of time, or elementary period of time, let it be dt. Due to this, an elementary impulse is received by the body. Let us take it as a di. Let us take it as di. Okay. So when this impulsive force F acted on a body or an object to a very small or over a very small and elementary period of time dt, the object will be received an impulse of di. Okay, so now what I can write? Now I can write that the elementary impulse di is nothing but F into dt. According to this formula, I can write it di is equal to F into dt. Understood? Clear? Okay. Now with this expression, so this is the impulse is the elementary impulse. Elementary means what do you mean by elementary? That means small. Okay. So now suppose I have to find out the total impulse. I have to find out the total impulse for a time period t1 to t2. When this force is applied on an object, suppose I have to find out the total impulse for a time period t1 to t2. Then what I can write? I can write I is equal to integration f dt from t1 to t2. Very simple. I have to find out the integration. The total impulse. I is equal to this much. Clear? Understood? Give equation number 1. Clear? Okay. Now from Newton's second law, listen very carefully. From Newton's second law. Okay. So from Newton's second law, what we will know? Now the force is equal to rate of change of linear momentum. F is equal to dp by dt. We know that. Clear? So that implies dp is equal to f dt. We know that dp is equal to f dt. All clear? Okay. So now give it equation number 2. Now we can substitute the equation number 2 in equation 1. Now we can substitute equation 2 in equation 1. So you have to write down by substituting equation 2 in 1. So what I will get by substituting what I will get? Now I will get very simple. The total impulse I is equal to In place of, look at here, in place of f dt, I have to put dp. I have to put dp. Clear? So now the range is also changing because here the variable is dt. That's why t1 to t2. Here the variable is tp. So that's why p1 to p2. Understood? That means the momentum initial to the momentum final, p1 to p2. Clear all of you? So what I can get? Now that implies I is equal to, so integration of dp is p, ranges from p1 to p2. That is equal to, if I will solve this, then I can get upper range minus lower range. Look at very carefully. So this is finally we will get, that is the, what you will get? What you will get? Given equation number 3 is a very important conclusion I will get. Very important conclusion I will get. Okay. So what the equation number 3 says us? Now equation number 3 says us that the change in momentum is nothing but your impulse. Okay, so this is a very important relationship between impulse and momentum. Listen very carefully. So the change in momentum gives us impulse. I is equal to p2 minus p1. Understood all of you? Okay, and this equation number 3, this derivation what I have derived, this derivation is a very important derivation or the important relationship between the impulse and the momentum. I is equal to p2 minus p1. Clear all of you? Okay, so this is about your impulse. Impulse, and this is the description, this is the relationship between your impulse and the momentum. So change in momentum, when the momentum is change in between two period of time. If the momentum at time t1 is p1, if the momentum at t2 is p2, then what will be the impulse? The impulse is I is equal to p2 minus p1. Clear? I think all of you clear about this one? Clear all of you? Okay, so that's why this is also reason is that when a player, a cricket player or fielder, okay, going to catch a ball, he or she will have to lower his or her hand to get less hurt. Understood all of you? Okay, so this is all about our discussion for now, for this class or for this session, that is conservation of linear momentum, impulsive force and impulse. Thank you so much. Okay, have a good day.